And you should see it as much. Yeah. I mean, it might be like my advice yeah, I just
everyone. Barna Saha will now be speaking. She's a professor at the University of San Diego. She's been doing a lot of cool work on edit distance, among other problems, and she'll be telling us about how to compute edit distance in the fully dynamic model.
Thank you, Julian. So it's great to be here. And so I'll be talking about edit distance in the fully dynamic model. And this is a joint work with my ex-postdoc, Tomasz Koszymaka and Anish Mukherjee. So what is edit distance? I guess all of you know. So it's a very fundamental measure of computing distance between sequences introduced way back in 1965 by Levenstein. So basically, you're given two sequences. You want to know what are the minimum number of edits, insertion, deletion, and substitutions are required to convert one sequence into another. So for example, if you have two sequences like this, here, if you're deleting B, then you're substituting this B with an A, and then you are inserting B over here, or deleting B over here or inserting B over here. Then with 3 edits, you can convert X to Y, so the edit distance between X and Y is 3. It has a lot of applications, comparing DNA and RNA sequences, comparing languages, text, communication streams, et cetera, et cetera. So how do you compute edit distance? This is something you learn in an undergraduate course. So basically, you can write the first sequence here and on the top, and the second sequence on the left. You can do it using dynamic programming, but here is another way of viewing the dynamic programming to compute edit distance. It's like this is your grid-like graph, and here on the horizontal edges, so each node has 3 edges, horizontal, vertical, and diagonal. On the horizontal edge, you have all the horizontal edges have weight 1. What does that mean? That means like you are deleting B, deleting B, deleting A, deleting B. So these are deletions over here, so cost 1. So all horizontal edges have cost 1. Similarly, vertical edges means deletion over here. So all the vertical edges have cost 1. The diagonal edges might have cost 0 or 1 based on whether the two symbols matches or not. Like here, B and B matches, so the cost is 0. Here, A and B, they don't match, so the cost is 1. Okay? So you have this grid-like graph, and then the edit distance is simply like computing the shortest path from this point here to here. Okay? And this can be done. This is like n squared nodes, n squared edges. So here, if you do this, this will be your shortest path, and you can compute the edit distance in this shortest path on the grid graph can be computed in n squared time. So you can compute the edit distance in n squared time. And this is also optimal considering the strong exponential time hypothesis. Okay? So these rates show that where the edits happen. So there is a deletion here, there is a substitution here, and there is a deletion here. Okay, so now we are considering the dynamic model. So what does the dynamic model means here? Like in the dynamic model, we are first given 2 strings X and Y, but now we are allowed to make changes on the string. So you can substitute symbols in X or Y. You can insert, you can delete, and those positions could be arbitrary. It could be at the beginning, it could be at the end, it could be at the middle, anywhere is possible, okay? And you have to maintain the edit distance. very fast with these dynamic changes. So it could be the applications could be like genome sequences, they go through mutations, documents, they go through revisions, et cetera, et cetera. And we want to trade off like the goodness of estimate, what kind of estimate you can give for edit distance with the update time. Okay, so this is your dynamic edit distance problem. Now, if you look at the dynamic programming table or this shortest path computation here, if you make even little change, like if you make a substitution here, like all these diagonal edges are going to change. So lots of entries in your shortest path, in your dynamic programming table or the shortest path computation actually changes. Or even worse, like if you make some deletion, it's possible like everything changes, okay? So you cannot really simply take the dynamic programming computation or the shortest path computation and try to make them dynamic. So what is known here in the dynamic model for computing edit distance? Well, previously, most of the works had considered restricted models. In the restricted models, the edits are only allowed on the either end, okay, either at the beginning or at the end. And there has been some work that does that, and they still require linear update time, and they're computing things exactly, but the model is restricted. The fully dynamic model, as far as we can tell, the only considered in 2020, where the update time is still linear, and you can return an exact answer. But this linear is the best that you can hope for. Because if you're considering, like, you can insert one at a time, like you can, with n updates, you can construct your entire string. So if you can get anything better than n, then even in the static setting, you will get something better than n squared, which is not possible using the strong exponential time hypothesis. Therefore, linear update time is the best possible when you are trying to compute edit distance exactly. Okay? And there are other models that had been also very well studied in edit distance computation, like streaming and so on. So the question that we are really asking here, okay, so for exact computation, I need linear update. So what about approximate computation? There has been tremendous progress on approximating edit distance in the last 2 decades. So the question is, can we utilize that progress and get something significantly sublinear update time for approximating edit distance? Okay, so that's what we are asking. So right now, what we know, we have a constant factor approximation that runs in near linear time by Anduni and Nozaski from 2020. We have a 3+epsilon approximation that runs in subquadratic time. Then there has been a lot of progress on sublinear time approximation of edit distance as well. So the question is, can we utilize the progress in fast approximation algorithms for edit distance to get a good dynamic algorithm for it? Okay, so this is a valid question. And we will see what we can do. But before we do that, like, let's go back. So so this is what we are trying to do. We are trying to use these algorithms as a black box and get a fast dynamic algorithm for edit distance. That's kind of the first thing that we are trying, okay? So even to do that, we have to go back a little bit, like not a little bit, we have to go back work like way in 80s to understand another algorithm for edit distance, which computes edit distance exactly. It looks at the dynamic programming table, but actually the algorithm is a greedy algorithm. Okay, so that utilizes what is known as LC queries, which is longest common extension. So what it does, it computes the farthest row with cost 0, 1, 2, and so on. Okay, so you are starting your computation right over here, and you are asking, how far can I go with cost of 0? Okay, so how far can you go? You can follow this diagonal, B and B matches, so you can go up to here. But if you try to extend anywhere here, you will incur a cost. So this is the farthest you can go with cost of 0. Okay, so after that, you are asking, how far can I go with cost of 1? So what can you do here? You can come over here, right? Pay this substitution here. But then if you want to progress, you will get stuck. Or you can pay a deletion here, and you can try to follow this 0 weight path, right? Or you can do a deletion here, and you can try to follow the 0 weight path over here. So you can try to do this, and this is how far you can go with a cost of 1. Okay. So now here you are asking, how far can I go with a cost of 2? So what can you do? Like you You can come over here, but then you get stuck. You can come over here by doing a deletion. You again get stuck. You can come over here. You get stuck. You can come over here. Now you can follow this zero length path up to here and so on. Okay. So this is how far you can go with cost of 1. Then cost of 2, you can in fact reach over here. And then with cost of 3, you will be reaching here. Okay. So this is a greedy algorithm that computes the edit distance. And what you see here, that if you're trying to understand whether your edit distance is bounded by some small k, then your computation only needs to consider k diagonals on the top, k diagonals at the end, below, around the main diagonal. Okay, and in each diagonal, you are kind of keeping track of these points like cost 0, cost 1, cost 2, cost 3, and so on. So you are keeping track of k points in each of the 2k plus 1 diagonals. Okay, and between these points, what do you have? You have like a matching substring here, like all 0 cost. These are called LCE queries, or longest common extensions. So this is the part where you have exact matching. A matches with A. So these are your longest common extension. So if I tell you I can pre-process the string so that I can answer this longest common extension queries in constant time, then what is the running time of this algorithm? Well, you have 2k plus 1 diagonals, and in every diagonal you have k such points. Like you have to ask this LCE queries k times per diagonal. There are 2k plus 1 diagonals. So overall, you have to ask for LCE queries k squared time. Okay, so that gives you n plus k squared time algorithm, n plus k squared time algorithm for computing the edit distance. And it also tells you if you allow for pre-processing on the back end, then in k squared time you can compute the edit distance exactly, which is great if k is small, but obviously k could be large, and in that case you are still heading the n squared time. One advantage of this algorithm is that this pre-processing the data structure for LCE query, you can maintain it in the dynamic way. So even when the strings are going through updates, you can maintain the data structure for LCE queries. And after that, obviously, you can run this algorithm in k squared time. So this algorithm, back from 1988, actually works in the dynamic setting with an update time of k squared, which is great for small k, but not so good if the k is large. So what is our first thing that we are going to do? Like, we are going to use this algorithm when my k is small. And when my k is large, I'm going to use the recent developments in the fast approximation algorithms for edit distance. Okay, so here we are trying to use these algorithms as black box, and we are trying to see how far can we go using them as black box. So what we do, so when the distance is small, we'll be running this order k square algorithm, but we do not need to run this order k square algorithm after every update. If you are allowing, say, constant factor approximation, we can run it after every k update. Okay, so since we know, like, since we are trying to say that k and 2k are fine, so it's not that we have to run this k square algorithm after every update. We can run it after every k update. Okay, so then the amortized time, update time, becomes order k. So that's from the algorithm that I just showed you. So this achieves constant factor approximation, amortized time order k. But now when k is large, what we will do, we can run this Andoni-Nozaski's algorithm that runs into the 1 plus epsilon time. But again, we will do that after every k update.
What is epsilon here?
So this epsilon depends on the approximation factor. So if the approximation is some function of epsilon, okay, 1 over epsilon. And if you want, like, not constant factor, but some into the C approximation, you can in fact run a sublinear time algorithm after every k updates, which has a running time of into the 1 minus 2c. So that's first thing that we do. And now you have to balance, like if you are using Andoni-Nozaski and the small distance you are doing this, large distance you are doing this, then you just balance k with this, and that gives you amortized update time of n to the 0.5 plus epsilon. This is for constant factor. And if you want to do n to the c approximation, you balance k with whatever is written here, and that will give you amortized update time of n to the 0.5 minus c. Okay, so what you see here, that using the state-of-the-art known algorithms as black box, the update time times approximation factor is n to the 0.5. Okay, so now the question that we are asking, can we do better than this? So our response is as follows. So what we do, so we reduce the update time times approximation factor from n to the 0.5 to any arbitrary n to the epsilon for any arbitrary epsilon greater than 0. Okay. So in fact, what we get, like given a parameter b, so this is going to be our update time, which is b squared log n to the power log bn, and this approximation factor is b log bn. But if you set the parameters properly, then you will get a update time of n to the epsilon for an approximation factor of polylog. You will get a subpolynomial update time for an approximation factor of subpolynomial approximation factors and so on.
You say the best approximation factor is polylog. Is that, do you have an algorithm for this, or that lower bound?
No, we have an algorithm for it. So what I'm trying to say here, yes. So I didn't explain this line. So the algorithm that we give, so I'm saying that the update time times approximation factor of our algorithm is n to the epsilon, with the caveat that the approximation factor, the best approximation factor that we can achieve is polylog n. So we cannot go down to constant factor, and that remains as one of the main open question after our work. Okay, so the best approximation factor that we can achieve is polylog n, but then the update time is n to the epsilon. Previously, using the black box, for even with all the recent developments, what you could achieve is n to the 0.5. Any question so far? So the problem definition, the model are okay, right? So now we are trying to develop. Now I will try to tell you some of the high-level ideas about how you get to that. There's n to the epsilon update time with polylog approximation. So first of all, if I'm trying to design a good dynamic algorithm for not only just edit distance, maybe for anything, I would need to find some small independent problems so that from their solution, I can get a good estimate of my final thing of edit distance. Okay? So maybe what I can do, I can take my x, I can start partitioning x into smaller and smaller parts until it becomes like one element at the leaf. So this becomes a tree. And then I will take each of these small parts and I will try to compare it with some suitable subpart of y. Okay, so that could be one way of partitioning x. So you will compare parts of x with appropriate parts of y, and I will partition x. Okay, so that could be one way of breaking into independent subproblems. And another property that I should have, that when an update happens, it should not affect too many of these independent problems. Okay, so if an update happens here, it should affect only a few problems, few subproblems. If an update affects here, it should affect only a few subproblems. If you have these two properties, then there is a hope that you can come up with a good dynamic algorithm. So update does not affect too many subproblems. So we tried to see, like, is there any work out there for static algorithms for approximating edit distance that has this property? And we had to go back quite a bit to 2010 to see that indeed there has been a work by Anduni, Krautgamar, and Onak who introduced this notion of tree distance that kind of has this fill. Okay, that kind of has this property. And in 2010, this was a big result. Like they achieved the first near linear time algorithm for polylog approximation. Okay, so and then after that, there was a long hiatus till 2018 when people came up with constant factor approximation, but in subquadratic time. And now finally, we have constant factor approximation in near linear time. But at that time, this was a big result. And this seems like out of all the static algorithms, much more amenable for dynamic version. Okay. So what is tree distance? Again, for tree distance, so I have to define tree distance. So what is tree distance? You take x, again, you keep on partitioning x into smaller and smaller parts until you, at the leaf level, you have just one entry. Okay, so you build this tree. So here this tree is binary. I'm showing it binary, but actually this binary won't work at all. You will have a much higher arity of the tree. Okay, so you decompose this X. Now you take a node V. So this V represents an interval I to j. Now I have to tell you which part in Y I should compare V with. So that's given by the shift S. So when I'm telling you I have a node V and I have shift S, that means this node V represents an interval ij in X, and that's compared with I plus S to j plus S in Y. Okay, same length here, just shifted by S. So the tree distance will be represented by this tuples V and S. V is a node, S is a shift. Okay. So now how do I define it? At the leaf level, if you have node I here, and so you'll compare xi with yi plus s. So these are just single entries. It will be 1 if they don't match, and if it will be 0 if they match. So it's basically Hamming distance. So it's just one entry. Okay. And for the internal nodes, I will be defining tree distance recursively. So what do you do here? If you are at an internal node V, you will be looking at its kids, its children, V0, V1, so on. And you have this shift S, right? So V is saying, hey, compare me with these, if it's ij, I plus s, j plus s, mean y. So what the children will do, the children will look at this shifted, this interval shifted here in y, but it will not just consider shift S, it will consider all possible shifts. It will consider all possible shifts as 0. So V0 will consider all possible shifts as 0. It will look at whatever the tree distances has computed recursively, right? But now you have to pay for this. If S0 is not S, you will pay for this here. Okay. Similarly for V1 will consider all possible shifts S1, but if S1 is not matching with S, you will have to pay for it. So that's what the tree distance is. So you are basically looking over all shifts for your kids, and you are saying for which shift I get this as minimum, and then I'm adding up over the children. So this is how the tree distance is defined. Okay. So at the leaf level, it's just Hamming distance. At the when you go up and up, you define it recursively. So for each kid, each child, it's looking over all possible shifts S0. But whenever S0 doesn't match with S, you have to pay for it here. Similarly, S1 will be going over all possible shifts. Whenever S1 doesn't match with S, you have to pay for it. And then this is it. Is this okay? Okay, so the first question, when you define tree distance, you have to ask, okay, you have defined distance, what is its relationship with edit distance? So what was shown in this AKO 10 paper is that tree distance is always greater than edit distance, but it also bounded by b times d of edit distance. What is b? B is the arity of the tree, and d is the depth of the tree. Okay. And if you're considering a balanced complete tree, then d is log bn. So basically, it will be bounded by the actual edit distance and b times log bn of the edit distance. And what is this TDT? Is basically you are looking at the root. Root means what? Root means like entire x. You're looking at shift 0 because you have to compare entire x with entire y. So this is your tree distance at the root with shift 0, xy, and this is bounded by edit distance to b times log bn of edit distance. Okay, so that's the relationship between tree distance and edit distance.
Is there some intuition for like why tree distance was defined in the first place, or like what is it trying to capture?
So the tree distance, like, oh, okay, so first of all, like we're trying to decompose it into these independent parts, so it really helps in the computation. But one of the difficulty in handling edit distance is like the shifts, insertion and deletion that causes the shifts. Okay, so here in the tree distance, like if you're not considering shifts, it's Hamming distance, but you're really paying for the shifts when you are considering like you are going from S to S0, S to something else. And so overall, like it gives you a decomposition into independent problems. It handles the shapes in a nice way, and you get this approximation factors, which is bounded by the additive of the tree and the depth of the tree. Okay, so that's the relationship. The next question is about efficiency. Okay, so you define tree distance. It gives you some approximation for edit distance, but how efficiently you can compute it. So first of all, so I said that our main goal here is to know whether my edit distance is, say, below small k or above capital K, where capital K is this approximation BD times K. Okay? So now that means I really want to know whether my tree distance is less than capital K. Because if tree distance is greater than capital K, then for sure I know edit distance is greater than small k. I can return no. And otherwise, if tree distance is less than k, capital K, then I know my edit distance is less than capital K, and I can return yes. So really the problem that we are trying to solve, whether my tree distance is less than capital K. Okay? So previously I was saying, hey, look at the children, consider all possible shapes. But actually, we do not need to consider all possible shapes. It's okay to consider the shapes around plus minus k around S. Because if you consider anything more than that, you will be paying more than k here, which means your tree distance will be greater than capital K. So anyway, it's a no. Okay. So that means like I can cap my shifts around plus minus k around S. Okay. So this is called capped tree distance. But is this enough to get a good algorithm? No. Because like, okay, so this is the definition of capped k distance. So now you're looking at the shapes plus minus k around small s. And you are capping it at k as well. So this is your capped tree distance. But now even with this capped tree distance, if you're looking at the leaves, how many leaves does it have? It has n leaves. You have to consider k shapes around each of these leaves. So which means your computation even at the leaf level is order nk. And if your capital K is too large, then it's very expensive. Okay? So you cap it, which is great, but just capping doesn't help you to get a good efficient algorithm. So then what do you have to do? Well, yes, now you have to approximate tree distance as well. So tree distance is already giving you an approximation of edit distance. But just computing tree distance exactly is not too helpful. So you have to approximate tree distance as well. So maybe 2 approximation or any constant factor approximation for tree distance is fine. So let's just do that. So what we'll try to do, we'll try to get an additive approximation for tree distance. Okay. So beta v will be the additive approximation at node v. So how much additive approximation can I allow at the root if I'm looking for, say, 2 approximation? That's a question for you. So I want to know whether tree distance is less than capital K. Now I'm allowing 2 approximations, so it's okay. Like if it's k to k, it's fine. So then I can allow an additive factor of plus k, right? Or some constant times k at the root. So I can allow additive factor of plus k at the root. And similarly, so let's define this beta v to be the additive approximation that we allow at node v. Okay. So how do you do that? Like what we are going to do, we saw that considering all possible shapes is a problem. Like if you're considering all k shapes, I have to pay nk at the leaf level. So what we are going to do, we are going to consider a subset of the shapes. We will be considering shapes only at an interval of beta v. So we are not going to consider all shapes. We are going to consider shapes at an interval of beta v. So how much additive factor does it add to? Like if it happened that the optimal is wanted to select this shape, I'm not considering this one, but I'm considering something nearby within plus minus beta v. So I'll be paying that in my in here. So we will be off by plus minus constant times beta v. Okay, so plus minus beta v. So we will be considering about k over beta v shapes to get a beta v additive approximation. So my running time will be roughly proportionate to 1 over beta v when I'm considering beta v additive approximation. Okay. So the question is, okay, at the root, I can allow an additive factor of k, or at the node v, I can allow a beta v. But then how do I distribute this additive factor around these kids? So what would you do? So you are trying to additively approximate the tree distance of every node. What I said to you, that at the root, I can allow for an additive factor of capital K. Now say the root has b children. What do you think should be the additive approximation factor at this b children that where we can allow?
Just divide by b.
Just divide by b, right? Distribute it equally among its kids. If you do that, what happens to the additive factor at the leaf level? You're starting with capital K, which was much less than n. You have n kids, n leaves, right? You are dividing equally, so it will be much less than 1, right? Which means at the leaf level, you have to consider all k shifts, which means you have to pay nk. It doesn't help. So there comes this very nice idea of precision sampling lemma from this 2010 paper. Actually, the precision sampling lemma has a root in streaming literature for computing frequency moments, heavy hitters, and so on, which basically says, like, you can allow for much larger additive errors. So you have to allow for much larger additive errors than simply dividing this beta v equally. Because at the leaf level, you need to have much larger additive error. You cannot say, hey, at leaf level, my additive error is less than 1. So the precision sampling lemma says you can allow much larger additive error at your children, but still, when you add up these estimates, you will get a beta v additive error at your parent. So the precision sampling lemma, so it's like it says that there exists a distribution. In fact, exponential distribution works. You will be selecting some precisions, u1, u2 to ub, independently from this distribution. And then you will be setting the additive factor at your children, the hth children, beta v times the precision. Okay, so this is how you will set it, and what is the expected value of this 1 over uh is polylog n. Okay, so let's process this a little bit. So what is my beta vh? Beta vh is beta v times uh, so which means beta v over polylog n. In fact, you can think about it as log square n. Okay, so the beta vh is beta v over log square n, and your b is going to be much larger than log square n. So essentially, you are getting much higher additive error here, and over the depth, your additive error is going to increase by log square n whole square. So at the end, you will get log n over to the power order of d at depth d. Okay, so this is how your additive error decreases. So it doesn't decrease by too much. So the expected running now, and if I'm looking at expected running time, I told you my running time depends on 1 over this beta vh, because my shifts that you will be considering is k over beta vh. So it's really proportionate to this. So this becomes like, so basically your running time increases again by a factor of log square n at every level. So overall, your running time becomes log n to the power log bn, because that's your depth, and you do it over all nodes. So your running time is n times log n to the power log bn. And if you set your b to be log n to the power border of 1 over epsilon, as you can see, your additive is really large. Okay, so then your running time becomes n to the 1 plus epsilon. Your overall approximation factor becomes polylog. So that's your AKO algorithm. It's not quite the AKO algorithm though, but okay. So now I'm going to try to take this algorithm and make it dynamic. So how much time do I have?
About 6 or 7.
Really? Not till 15?
I mean, wanted to save time for Q&A, but you can go
Okay.
a little bit.
Okay. Okay. So the very first step to modify the static algorithm, well, we were trying to make the static algorithm pretty efficient. We did that using shift sparsification. So we need to use another concept of active node. Okay. So what is an active node? So we call a node active. So each v, remember, each v represents an interval. Okay. And you have a precision, which is telling you what additive factor is allowed at that node. Okay. So you will call a node active if that interval is greater than the precision. Otherwise, you will call it inactive. So what does that mean? So suppose you have an interval of length 5. Okay. And you say, hey, I can allow additive approximation factor of 10 plus minus 10 at that node. So then it's an inactive node because IV is less than beta V. So in that case, like if your interval length is 5, then you know the tree distance is bounded by 5. You can do all substitutions at that 5 elements. Your tree distance is bounded by 5. You are saying, hey, give me an additive, give me an estimate within additive factor of plus minus 10. Then 0 is a good estimate to return there. So for all inactive nodes, you can just return 0. So that means like you can prune away all the inactive nodes. You don't even have to handle them at all. So you only consider active nodes. And what we can show that the expected number of active nodes is actually n over capital K, this factor, this polynomial factor. Okay. So if you had just considered active nodes, so forget our shift sparsification. If I had shown you the analysis based on just these active nodes, I will say, hey, I will just do my computation only on active nodes. I will prune the inactive nodes, and I will consider all possible shifts. Now, all possible shifts are capital K. Then I would actually have still got the same running time as we got here. So in fact, you could have done this analysis for the static algorithm just using active node and not shift sparsification. In fact, I think that's what the EQ algorithm does. They just consider active node, doesn't consider shift sparsification. But for dynamic algorithm, you need to consider both shift sparsification and active node. We also have to modify this definition a little bit, so I will not bore you with that, like how you cap the tree distance, because the cap tree distance previously didn't allow like having some certain inequalities to hold at the internal nodes. But anyway, so we have to change the definition a little bit as well. So we have shift sparsification and active nodes. So let's look at the first step, okay? So the first step where we consider only substitutions in X and substitutions in Y. So that's a kind of a simpler case. We are not allowing insertion changes so we are considering edit distance, by the way. Just the changes that are happening dynamically, we are only allowing substitutions in X and substitutions in Y. So it has an advantage, like the structure of the precision tree, which is built on X, like you see some asymmetry here, right? This precision tree, like these, we are calling the tree precision tree because this so much depends on the precision sampling lemma, so we'll just call it precision tree. So the structure of the precision tree built on X, it does not change. What does that mean? That means at every internal node V, the interval that it represents, like I to j, that remains the same because you are just doing substitution. You are not doing any insertion deletion. So the structure remains intact, which is kind of an advantage. And our algorithm is very simple. Like it's saying, hey, recompute all the estimates for which the tree distance might have been affected by the substitutions. Okay, so this is our algorithm for when we are just handling substitutions. So then I have to tell you like how many nodes are affected by a substitution. Okay, so let's zoom in to these pictures a little bit better. So what we can show that if a substitution happens in X, then the nodes that are affected, they form a single root to leaf path. Okay, so only one node at every level. There are some, these orange nodes are basically telling you like, oh, these are not affected, but when you're computing the tree distance, you have to look at the children, so you have to look at the estimate at the orange node. Okay, so only these gray nodes are affected for a substitution at X. The substitution at Y is a little bit trickier. As I have told you, it's pretty asymmetric, like when you are doing this precision sampling tree. So substitution at y might affect more nodes at every level, but what we can still show that the number of nodes that are affected, if you look at the starting interval and the end interval, it's about order of k, order of capital K.
I've been confused by this the whole time. So can't k just be, like some fraction of n?
Capital K?
Yeah, or is that the approx factor?
So this is like, so you are trying to, so you really want this capital K to be as close as to small k, because you are trying to solve this gap version, edit distance less than small k or greater than capital K. Okay, so capital K, if you can bring, like, if you can have capital K to be 10 times small k, then you have a 10 approximation factor. Here our capital K is BD times small k because our approximation factor is B times D. Okay, so it's polylog times small k. Okay, and we are now looking at this tree distance problem where we are trying to find out whether my tree distance is less than capital K or not.
But so should I think of capital K as much smaller than n?
Capital K depends. So capital K is small k times the approximation factor. So depending on your small k, yeah, capital K is much smaller than n. Okay, so capital K is the approximation factor times your edit distance. Okay, so depending on what your small k, you will have your capital K. Okay, so anyway, so an edit in y will affect what we can show that it affects multiple nodes, but the interval that it spans is about order of capital K. Okay, so now let's look at like what happens. Like, so if you are looking at the leaf, that means it can affect capital K leaves, right? And if I am considering even one shift at these capital K leaves, my update time will be order of capital K, which can be too high. But what we can show that not too many of these leaf nodes are active. So you really need to use the concept of active nodes here to show really not too many of these are active, so it's fine. And you also need shift sparsification because even if you are looking at one node, if you have to consider all possible K shifts, then it's again too costly. Your update time is capital K. So you need both shift sparsification and active nodes. And after you do that, you can bound your update time to be polylog. Okay, so now let's look at the more challenging case. And in fact, this, if you understand this part of this modification, then after that, the fully dynamic one, you still require more ideas, but the main ideas are kind of here. Okay, so this second part where you are allowing substitutions in X and all possible edits in Y. Previously, we were allowing substitutions in X and substitutions in Y. Now I'm allowing substitutions in X, still substitutions in X, but all possible insertion, deletion, substitutions in Y. Okay, so the advantage, still the precision tree which is built on X, structure does not change. But now there is a big challenge here. If you delete one symbol here of Y, suppose you deleted the first symbol of Y. So basically then the string shifted, right? The Y shifted. So whatever you were comparing before, take any node in X, whatever you were comparing before, you were comparing it to something else, like this dark green, light green, okay? So it's like, this is a different segment than this segment shifted by one. So essentially, all your tree distance estimates, on all nodes, all shades should change if you make even one deletion in Y. Okay, so that's a big problem. So how do you overcome that? So to that, we have to bring in some more ideas. So what we do, so we observe that, okay, so ultimately what we are trying to do, we are trying to understand whether edit distance is less than small k or greater than capital K, right? So now if your edit distance is less than small k, then what we know that in your X and Y, there are k positions where edits happens, right? But beyond that, there is this k plus 1 segments which are exact matches, right? There exists a decomposition of X and Y such that there are k edit positions and there are k plus 1 segments which exactly matches. If I can obviously maintain this decomposition, I'm done. I don't have to do anything else. So we do not know how to maintain this decomposition dynamically, but we do know how to maintain this decomposition. So what is this decomposition? It still partitions Y into these k plus 1 segments, it still finds a matching segment in X, but these matching segments now can overlap, or there could be gaps. So from this, you cannot construct the edit distance, but you can still find these matching segments. Okay, so we do this dynamic decomposition, and that takes order k query time, order 1 update time. Okay, so that's your first idea. And the second one is now we want to estimate tree distance xy. What we maintain instead is tree distance between x and x. Okay. So we are estimating x and x, though we want to estimate x and y. How does that help? Okay, so we want to estimate x and y, right? So suppose I want to estimate tree distance vs xy. So I'm looking at node v. I should have been looking at I plus s, j plus f in y. So instead of that, let's look at a bigger interval, I plus s minus capital K, j plus s plus k. Okay, remember you have to consider sheaves which are within plus minus k. So what we claim that when we are trying to estimate the tree distance vs xy, where v is I to j, the only substring of y that is relevant for this computation is within this I plus s minus k to j plus s plus k. This is just coming because you have to consider shifts within plus minus k. Okay? If it happens that this substring is entirely contained within this matching region, that means there is a matching substring over x which exactly matches here. Okay? So this is just shifted by s prime. This exactly matches. So it happens that if I'm looking at the precision tree built on x and x, if I just change the shift from s to s plus s prime, whatever the tree distance you will get here will be exactly same as the tree distance as here. So we can just copy. And do you know how to maintain this x and x? You know by now. Because only substitutions are happening in x and x. So I told you like how to maintain the precision tree dynamically when only substitution happens. So you know how to maintain this. And at this point, you are just copying from that to get an estimate for xy. And if it happens that this region, which is relevant for me, actually handles this, actually contains this edit point, then you have to make some, then you have to recompute. But there are not too many such edit points. There are only k of them. And as we have shown you here, that with one edit, not to whatever is affected, we can handle it. So with k edits, it will be just multiplied by small k, and we don't have to do this computation every time when an edit happens. We can do it after k edits. We can do it in a lazy fashion. So on amortized, your update time will still remain. Okay. So obviously, I didn't tell you how to handle the fully dynamic case, but fully dynamic case uses the same data structure as in the substitution in X and insertion deletion in Y. It has to do some more work because in that case, because you're allowing insertion deletion in X, this also becomes unstable. So you have to work with some uniquely leveled strings and so on. But the main idea really is embedded in the case where you have substitution in X and insertion deletions in Y. Okay, so that's it. So we get the polylog approximation, like we often, this theorem, which gives you polylog approximation with n to the epsilon update time, or subpolynomial approximation with subpolynomial update time. Main open question, can you get a constant factor approximation in n to the epsilon update time? Lower bounds in the dynamic setting. Well, if you can get anything better than n to the epsilon update time, you will get better static algorithm. That would be great. But maybe there are lower bounds that in the dynamic setting, because it doesn't hold in static setting, maybe holds in dynamic setting. So what can we say about lower bounds? And so our bounds are on expectation. The update time bounds is on expectation. So can you make it high probability from amortized to worst case? These are like immediate kind of immediate questions, but the main open questions are here. Okay, so thank you.
Okay, so since we're short on time now, I think we'll take questions offline. If you have questions for Barna, please talk to her. And we'll be having a coffee break now until 11:45, so please come back at 11:45.